Hello, my name is Jared Saya, and I'm going to be speaking today on scalable and secure computation among strangers. And this is joint work with a large number of colleagues. So the work that I'm going to talk about today is motivated by permissionless systems. The basic idea in these networks is that um, IDs, nodes can join and leave at will, and they are large. And the fact that it doesn't require permission to join the networks generally means that there's a large number of Byzantine IDs, Byzantine or adversarial IDs. And our goal is to solve classic coordination problems like agreement and leader election and so forth in these models without having to send a quadratic number of messages. So keeping the number of messages small so that we can ensure that everything is scalable. The recent work in scalability of Byzantine agreement shows that in a standard model, so this is basically like if you have an all-to-all network and it's and you initially know everybody's ID to begin with, that you can perform these algorithms very efficiently in terms of messages. So you can send soft O of n messages total. And this work, as I said, just assumes the Kd0 model, standard model, where every good node initially knows the IDs of all its neighbors. So a very large research problem is, can we extend these types of results to networks where we have churn? In this talk today, I'm going to talk about one step towards this problem, which is to try to extend these results to what is called the Kd0 model, where basically you don't know all of your neighbors initially. So more specifically, in the Kd0 model, nodes don't know their neighbors a priori. They don't know the IDs of their neighbors a priori, but they do learn their neighbor's ID upon receiving a message from it. And there's a trivial quadratic bandwidth cost reduction from Kd0 to Kd1. Basically, if just in the first step you everyone just sends out a message with their ID. But obviously we want to avoid that because we don't want to send a quadratic number of messages. So this is the question that we'll be answering affirmatively today. So our model, to be a little more specific about it, we assume an adversary that is static in the sense that it has to choose the set of Byzantine nodes, the nodes that it will take over at the very beginning of the algorithm. It's rushing in the sense that it is allowed to see the messages that are sent out by the good nodes in each synchronous round before its own IDs need to send out their messages. And the adversary is computationally unbounded, which prevents us from being able to use cryptographic primitives. We make that assumption. Further, we assume that the end nodes all have distinct IDs in the range 1 to n to the k for some constant k. And we allow the nodes that are controlled by the adversary, the Byzantine nodes, to choose their own IDs. Finally, communication is assumed to be synchronous, and the network is assumed to be fully connected. This is our main result. So we have an algorithm that solves Byzantine agreement, leader election, committee election in the Kd0 model with polylog n latency. So that's the number of rounds is polylog n. And O of t plus n log n expected messages, where t is the the minimum of n squared and the number of bits that are sent by the adversary, by the nodes controlled by the adversary. So in particular, if the Byzantine nodes are sending 0 bits, then we send very small number of bits, soft O of n. And if the Byzantine nodes send a quadratic number of bits, then we send no more than n squared log n total bits. We can tolerate any fraction bounded away from 1/4 number of Byzantine faults, and our algorithm succeeds with high probability in it. Further, our latency bound holds even in the congest model, where in each round, every link, you can send a message over it that just has poly log n bits in it. One further additional property, interesting property of our algorithm is that when nodes write to unknown IDs, what we can think of, what we call strangers, there's only two primitives that they use to do that. One is that they send a message to a random stranger among all the strangers that they currently know. And then the second is they broadcast to all strangers. So this is sort of an additional potentially useful property that our algorithm has. Before I give you some of the details about the upper bound, let me just give you the most important lower bound. So among fast algorithms, like our algorithm is, so algorithms that take just poly log n rounds, we can show that our message cost is tight to within log n factors. And this follows from this classic result, which shows that you need omega nt messages when you have t less than or equal to n bad nodes. This is true for both deterministic and randomized algorithms, this lower bound. And then the observation, simple observation that in the congest model, soft O of n bits can be sent by Byzantine nodes in poly log n rounds. That's the best that can happen, because basically, if a Byzantine node sends more than poly log n bits in a given round, it's unmasking itself. You know that's a Byzantine node. So thus, capital T, the total number of bits sent by the Byzantine nodes, is going to be soft O of little t times n. And so soft omega of t messages are needed for any poly log n round algorithm in the congest model. And this is true even for Monte Carlo randomized algorithms. So we also have some additional lower bounds in the paper. One is a lower bound for deterministic algorithms. Basically, it says that if you have t equals big O of n squared bits sent by Byzantine nodes, any deterministic algorithm sends omega t total bits. This is also true for Kt1. And we have a not tight, but sort of a non-trivial lower bound for Las Vegas algorithms, which is basically if t equals n to the 1 plus alpha, for alpha between 0 and 1, then the algorithm needs to send omega of n to the 1 plus alpha by 2 bits in expectation. Okay, now I will start with the upper bound for our algorithm. In this talk, I'm just going to focus on Byzantine agreement. In the paper, we also show how to solve leader and committee election problems. Our basic algorithm is that each node will become active with a certain probability, and these active nodes are going to try to solve Byzantine agreement. If they fail, then we're going to double the probability of becoming active in step 1, and we just continue in this loop until we eventually succeed. So step 2, the details of that I'll be going into soon will be, we're going to solve it via a solution to what we call the implicit agreement problem. Success will mean that strictly greater than t by n fraction of good IDs decide on the correct bit, and the remaining good IDs do not decide. And failure means that no good ID decides. And we have to do one of these two things. There's no in between for implicit agreement. And then you can ask, well, how do we detect if we fail or not? Well, that's what we use promise agreement for. So promise agreement is basically this problem where we're getting an output from implicit agreement, and success means that all IDs decide correctly, and failure means that no IDs decide. So basically every ID decides they need to continue. A little more details then about our algorithm. So we start off with this small probability of being active, and that probability is sort of our effort in some sense, as we'll be discussing. It's going to have an impact on the number of messages that are going to be sent by the good IDs. And once we solve implicit agreement, we then try to solve the promise agreement problem. And promise agreement either leads to success or failure. If we succeed, then we're done. We terminate and output the correct bit. If we fail, then we double our probability p, and we check to see if our probability p is still sufficiently small. If it is, then we go back to implicit agreement. So we continue the loop. And if it's not, well, then we just give up and do heavyweight Byzantine agreement, because we already know that the adversary in this case has sent a very, very large number of messages. So we can afford to send a large number of messages ourselves and still meet our theorem statement. So one important property of this implicit agreement problem is that if the adversary sends less than or equal to p(n squared) messages, then it's the case that implicit agreement will succeed. So this is the sense in which, like, as p gets larger and larger, the adversary is required to send more and more messages to prevent us from succeeding. So how does this work? Implicit agreement is sort of the hardest part of this algorithm by far. The idea, as I've stated, is each ID is active with some probability p. And as soon as an ID becomes active, it broadcasts this ID to everybody in the network. Then every active ID x maintains the set sx, s sub x. Initially, it's just a set of IDs that are received from all active nodes. Some of them may be Byzantine. Right? And then we're going to use the key idea here is we're going to make use of this subroutine, which may be of independent interest, called LargeCoreBA. And that is run among all of the active IDs. LargeCoreBA has this property that it ensures that you will reach agreement among nodes whose views mostly overlap. And it requires IDs in this range 0 to n to the k for fixed k. Here's kind of a picture of LargeCoreBA. So here I have the views of, there's 4 good IDs here. They have to contain a large core of good IDs. So this is this core G. Okay, so this is all the good IDs that are active that sent out their IDs in the initial step of our implicit agreement problem. This core, so in what sense is this core large? Well, it's got to be the case that if B is the set of bad IDs, so all this red region here, that B, the size of B divided by G has to be bounded away from 1/2. It has to be strictly less than 1/2. Okay? And if that's the case, then LargeCoreBA will solve almost everywhere agreement. So basically almost all of the nodes will reach agreement, and it'll solve it very efficiently. So it can do it in latency and per ID message cost, which is just polylogarithmic in the size of G plus the size of B. And it'll succeed with high probability in the size of G plus size of B. So this is like one of our core subroutines that we're making use of. Okay, and our paper shows one of the key technical challenges of our paper was to show this lemma. So even if we do have LCBA, though, there's still some technical problems, two key ones. So first, how does each active ID maintain a set SX to meet the LCBA requirements? And then secondly, how can the active IDs agree on whether conditions are favorable for agreement? To move forward. So for problem 1, we want to ask how we can meet the LCBA requirements. So a naive algorithm would be that ID X adds to SX every ID that it receives a message from in the initial broadcast step. But the problem here is that the adversary can make the size of B very, very large just by sending only A squared messages. So in particular, can make it equal to A squared. A is equal to n times P just by sending only A squared messages. So this is not, it's not an algorithm that scales very well with our effort if we do things this way. So instead, we're going to use non-active IDs to help out, to help us set these SX sets so that they don't get too large and they'll meet the requirements for LCBA. So what we need here is that we want B by G to be less than 1/2 unless the adversary sends omega of n squared times P messages. So our algorithm will be to make use of these other non-active IDs, and we'll call a good ID light if it received about n times P messages. So not too much more than the number of messages that it would have received if it only received things from good active IDs. Then light IDs send out information about their SX sets to IDs in the sets in those sets. So we can't send all IDs in SX, so instead we just basically will send a sample. So that's the idea. And the problem here is that the adversary can still easily make the set B, all bad nodes in SX, too large. So to deal with that, I mean, that approach, we need something a little slightly more sophisticated, which is a validation step. So each active ID X for each Y in SX, this is sort of the slightly smarter thing that we're going to do. It's going to query theta log n random IDs to see if they have Y in their own S set. And in that way, we filter out IDs from SX that are not in enough of these samples. So this requires the adversary to send out a large number of messages in order to mess up the conditions for our LargeCoreBA algorithm. Here's a picture of how this works. So blue is the active and good IDs, white is the good and not active IDs, and red is the bad IDs. And these IDs are sending out queries to theta log n random IDs in order to filter out the SX values. So the next big problem is, how can active IDs agree on whether conditions are favorable for agreement via our LargeCoreBA subroutine? So this is what we call the ready problem. So remember, in order to be ready, we need to have conditions favorable for LargeCoreBA, which means that this red region is not too big when compared with the blue region for all of the SX sets. So naive idea would be to use LCBA to determine ready. That is kind of the basis of our approach. The problem, though, is that some active IDs could run LCBA, but others may not have small enough SX sets to run it correctly. So our solution is we're going to have careful decisions about the input to the LCBA in order to determine whether or not we are ready. So each person will have a ready input, which is either going to be 0 or 1 based on the size of their SX set. And we will also make a decision about whether or not to run LCBA. And then finally, a decision about whether we will trust LCBA. And in particular, what will happen here what happens in our algorithm is that the IDs will sometimes run LCBA even when they plan to ignore the output, just to help out other IDs that are counting on them to run LCBA. And you have to be very careful. There's a very sort of subtle proof that we have in the paper about how this will all work out for correct parameter settings. So if the ready output equals yes, then the IDs will then run LCBA again to do agreement on a particular bit. And then finally, all active IDs will broadcast their ready bit and agreement bit. So here we have in the promise agreement, I'm sorry, in the implicit agreement problem, we're running LCBA for the ready out bit. This node has a very large SX set, so its ready input is set to be 0. And all of these the other 3 good nodes have ready inputs of 1. So everyone would run the LCBA algorithm in this example, and they will set their ready output bit to be something. Maybe they would all set it to be 1. Then if all those nodes that have their ready out bit set to be 1 will then run LCBA for agreement on some value bit. And then finally, the active nodes broadcast, all of the active nodes broadcast to everybody their ready out values and their value bit. This value bit is the bit that would be the output bit for agreement for everybody in the case where enough IDs have the ready out bit set to 1. Okay. So putting everything together for the implicit agreement problem, remember that we first have this validate step. I'm putting it in the top right here. And that helps us set our SX sets, filter out our SX sets so that they don't get messed up unless the adversary sends a large number of messages. And then we do the LCBA for the ready out bit. Then we do the LCBA for the value bit. And finally, the active IDs broadcast their ready out value. Okay, so now that's implicit agreement. But we still have to do something, right? So at the end of implicit agreement, we ensure that either greater than T by N good IDs decide or no good IDs decide. So we still need to figure out what to do next. And it turns out this is actually pretty easy. So this is the promise agreement problem. And the basic idea of promise agreement is just everyone samples. It's pretty easy compared to implicit agreement. The idea is that every good ID samples theta log n IDs to get their ready out, comma, value bits. And if you think about it, because of these properties being holding at the end of implicit agreement, the sampling alone is enough to ensure that at the end of the promise agreement algorithm, either everyone is going to decide on the correct bit, or everyone will will set their majority ready out value to be 0. So the entire algorithm then looks something like this. So remember, we initially set our p-value to be something small. We run implicit agreement. And then after that, we run the promise agreement problem and do the sampling. And at the end of promise agreement, we will either all the good IDs decide on the same value. They either all decide that they failed in this epoch, in which case the probability gets doubled, or in the lucky case, they all decide that they have succeeded, in which case everyone just terminates and outputs the value bit. In the case of failure, we just check to see if p is still sufficiently small. If it is, then we continue with implicit agreement. If it's not, then we throw up our hands and we run a heavyweight Byzantine agreement protocol. So in conclusion, I've presented an algorithm that can solve Byzantine agreement in the Kd0 model with O of polylog n latency, so it's fast. And the number of expected messages is O of t plus n log n. So the number of messages also is small in the case where the adversary does not send that many messages itself. So the number of expected messages scales nicely with the number of bits that are sent out by the adversary. So as I stated initially, and as you can tell from the algorithm that I presented, communication with strangers only occurs via broadcast to all strangers or writing to a random stranger. Finally, we have almost matching lower bounds for polylog n round algorithms in the congest model. And we have a non-trivial lower bound for Las Vegas algorithms, no matter how many rounds they take. Many problems for future work. One obvious problem is closing the gap between the upper and lower bounds for the number of messages sent for randomized algorithms. So we have this one non-trivial lower bound for Las Vegas algorithms that take any number of rounds, but it doesn't exactly match our upper bound. And then secondly, can we adapt our algorithm to better handle churn in permissionless networks? So can we take the very next step, going from Kd0, this Kd0 model, to something where maybe we're handling some nicely defined notion of churn in the permissionless system? And that's the end of my talk. Thank you so much for your attention. And please email me if you have any questions at all.